Okay, so we are recording. Okay. All right. So in the previous video or lecture, I discussed what the process of creating the vocabulary, right? So the intuition that we need to do a first pass and a second pass to figure out the vocabulary. So hopefully that concept makes sense. So now we're just going to mechanically go through the code. I do stress again, Huck Finn, the code that you have to use for the project or the homework, does not include tick token. Okay. But I've intentionally done it this way so that you guys, can incorporate it yourselves. Okay. So that will be, but I do have a simple example of tick token here. So I'm going to be using it. Yeah, which is that one. All right. So I think we had started with this with our Jupyter notebook. So I do have like some random things in here, but this we've covered already. This is just iris, the matrix multiplication. So we've got guys over there. All right. So we've got tick token, right? I think we imported it already. I'm going to run it again. I have it available. So you could run BPE through all the data that you download and create your own vocabulary. That's certainly something you could do. Or you could just use an existing vocabulary, right? So for instance, GPT-2, right? So that's what I'm going to demo here. There are other ones. I'm sure there's a Llama 3.2 and whatever. So all these have essentially, they've taken the data, run them through the BPE algorithm, created an optimal vocabulary to use of subwords. In my example, I'm just going to take GPT-2. So to demonstrate, you can see that here. These things are called tokenizers, essentially. I'm going to run it. Might take a second. Oh, it's done. You can see I'm grabbing GPT-2. GPT-2 is, there's, GPT-5 just came out, right? I love GPT-4o. I'm one of those people that's complaining about GPT-5. I don't know if you guys know about this, but GPT-5 just it's like off-putting somehow. It's very strange. And GPT-4o is very warm and very, there was like a feeling kind of thing going on. It was like very understanding about things. I liked how it explained things. I think GPT-5 over-explains. I'm overwhelmed by everything that it says. So I still use 4o. But anyway, those are the state of the art currently of OpenAI. I know they just released some open source GPTs. I haven't played with those, but there are new ones that they just recently released. But that's like state of the art. GPT-2, GPT-3, these are older, right? Certainly GPT-2 was not as great, but it's one that is used extensively. And the reason being is that the size matters, okay? So if you want to, let's say that even if you had GPT-4, where are you going to run it? You see what I'm saying? So, how are you going to train that? It's very massive. Whereas GPT-2, it actually has a smaller footprint while still being big, right? And it is a fully trained model. So it was trained on a lot of data. So again, I have all these like hopes that someday someone will be able to get GPT-2 to be as good as GPT-4o because they'll figure something out. You know what I mean? Like the data might be there, the signal, you just have to bring it out. But for now, it's not such a great model to use. And that's why we need to use like the 3.5 version or the equivalent Llama 3.2. But anyway, for our scenario, my examples, usually I select GPT-2 because of the footprint. I'm running on a laptop with no GPU, for instance. All right, so essentially how this works is I take tick token library, and then I say get encoding, and I have now a tokenizer. So remember that all this step or phase is about is taking actual sentences and converting them into subwords, like these syllable type things. Okay. So that's now, if you remember in all my previous examples, I started with like a sequence of integers, but they were all just random values. I had these tensors full of random values. Now you have the capability to have start with actual text, sentences, and so on, and converting them to the integer values. So here, let's try an example. So I'm going to take this one over here. So hello, do you like tea? That's the text. So I'm going to just run it. And remember that our goal is to just convert it into integers. So that's what I'm going to do next. So essentially, it's pretty straightforward. We take the tokenizer, and it's got these functions called encode and decode. So I'm going to take tokenizer.encode, I take the text, and then I print out the integers, and that's it. Do you guys see that? But these are actual proper integers, right, that represent something really important. So you can see here, 11, what is that? So we have a way to look up all these IDs, but essentially, it's one of the subwords in here. Okay. Yeah, so that's an example. So let's do another one. So I have two sentences here. So I have hello morning, do you like tea? And then I have I am good, thank you. So text one and text two. So now let's proceed to encode both of these into the integers. Okay, so essentially, if you notice, we're not using BPE to obtain a vocabulary. We're just using an existing one. But GPT-2 did look at all the text in the world, right? And so I think that should give us good subwords at the time when it ran. So now I have integers 1 and integers 2. So I can print integers. Okay, there they are. And I can print integers 2. You can see that I have another sequence of IDs. And so each one of these, if you remember, is a sentence, essentially. So now, that's exactly what I'm going to do. Do you guys see that? I just created a tensor. It's definitely n, right? So it's n, which is 2. But we have a problem. And the problem is that they have variable length. Do you see that? Because the sentences are different. So remember that to solve we can't have that when training a large language model. We have to have matrices of equal size, right? So we have to then do some kind of padding, right, to make sure that they are 2 by 40, right? And then each one of these, like 345, 588, through the embedding that we saw last week, will be converted to embeddings of size 512, so that we end up with a tensor that is 2 by 40 by 512. Remember that? So that's essentially all that needs to happen there. Okay. So here, the padding, we just need to add some padding, as you can see in this example, just so that they have the same size. Now let's reverse the process and convert the integers back to strings. Okay, so here, tokenizer.decode integers, and we just get hello, morning, do you like tea? Okay, we can play with these a little. I'm gonna take the longer one. Oops. Okay, so going to Control V. Yeah, I'm going to say vowels. Okay, I'm going to run vowels through this. Okay. So good. So let now, so this one had two 11s, I guess. What is integers? Oh, the commas might be 11s, right? Do you guys see that? Seems like comma is 11. Let's try. Do you guys see that? So that's exactly what is happening. It's just a simple yeah, like a dictionary, right? So we all know about dictionaries, but you can see the comma was given the value 11. Why? Because comma is fairly important and common in language. Um, let's take a look at another ID just individually. That one, it's pretty high value. Hello. So hello is an actual subword. Let's see. Hello, comma, morning. I wonder, see, I was talking about this one, right? ING. Let's take a look at what it did. That seems to be the word. Yeah, so it's using the whole word. I mean, that's how it works. But I'm trying to find one that might be broken up. 220. I don't know what this is. Space. That might be this space here. Try. Well, actually, let's go with the other one, this thank you one. So that should be these two. So let's try 2584. Yeah. See that KY? So that's essentially how it's interpreting it. So that's the idea. Okay. So you have these subwords um, that have these IDs. And given the subwords, which is through some algorithm it has created, right? Um, it's it's probably more capable of reconstructing a sentence and producing, things that look more like language. So that's why, I'm giving you tick token, and I'm going to, when we do the Huck Finn, we're going to do this with letters. I recommend that when you guys do your homework assignment, homework 2, try it with the letters and then try it with tick token and look at the output. And that might be a very interesting insight, right? That imagine that they invented GPTs, but they always only used letters for whatever reason. Like maybe the BPE algorithm was too complicated to invent. So then when we would get outputs, they would always be pretty bad. So today we wouldn't have almost AI. But then they invented something like BPE, which is totally outside of the GPT, and then all of a sudden it's amazing. You see that? So that's kind of my point. Okay. So it is the subword set is really important. And this is, another example of this is Morse code, right? So you guys probably have heard of Morse code. So like dots and dashes. So I think something like the X had a lot of dots and dashes, and then something like an E was just like a dot or something. So there's a similarity here, right? So the encoding of the language is a really important thing, which shouldn't surprise us. All right, great. So that's tick token. Are there any questions about it? If time permits, this would be towards the end of the semester. We'll look at BPE, but that's kind of something that's not a priority for me right now. So since I want to focus more on just the architecture of the LLM itself. Questions? All right. So oh yeah, go ahead. There's a what? There is an algorithm. BPE is an algorithm. Oh, another one? Yeah, I'm sure there are other ones, but BPE is the one that won. So you can think of it like when the problem existed, there were many people trying to solve it. So there's many attempts, and BPE uses actually parts of other algorithms that were good, but just not good enough. But it's a bit of a complex one. So it's not a trivial algorithm. So as I said, later on, I might cover it. All right. All right. So no questions. All right. So believe it or not, that's every single individual element of an LLM. We've covered everything, I believe. And now everything that new that comes in just has to do with putting the whole thing together. Does that make sense? So that's really what we're going to do now. And what I want to do now is go over the baby GPT. So we're going to look at the whole thing as an inference function from inputs to outputs and just complete this whole sequence. That would complete our how LLMs work repo, right? And then that would just leave the Huck Finn, which is the actual code, that the full implementation of a GPT. All right. So we're gonna do this one then, baby transformer. We can take a look at the notes first, just to kind of get situated. But I'll go over this idea. So remember, take a look at all the terminology, and then make sure you're reading the paper and the notes I provided. All right, so we're gonna do this one, baby transformer GPT style from scratch. This implements a super simple GPT style transformer block. So remember, this is just one block. But the beauty about this is tensor of n by 40 by 512 goes in, tensor of n by 40 by 512 comes out. So then you add the same block, you just repeat it, and then n 40 512 goes in, n 40 by 512 goes out, and then, just keep adding blocks, right? So that's something we haven't done yet. We're just focusing on one block. Imagine that inputs go into one block, and then it goes out to the end. That's essentially what we're doing. So this project implements a super simple GPT-style transformer block in PyTorch. It includes the token embeddings that we've already discussed, learned positional embeddings we've already discussed, a single head attention, which the QKV we've already discussed, a feed-forward layer, which we already discussed, and a final projection back to the vocabulary, which is the only thing I haven't focused, but it's very easy at this point. Okay? The objective is to build and run a minimal decoder-only transformer block for demonstration and educational purposes. The inputs are going to be the token IDs. The output logits over vocabulary. Remember this term again, logits. It took me a long time to understand this term. Like I would see logit everywhere in papers, and I'm like, what fancy equation do I need to learn to understand this? And as it turns out, a better way of understanding logits is a thing before the values are softmax or before the values become probabilities. It's like a step before that, and it's called logits. Okay, so we'll see that a little later in more detail, but essentially that's what I'm producing, just a final vector of values that will eventually be like a probability. From scratch attention and projection. So we've covered all these terms. They should be familiar to you. No NN transformer, not yet. Okay, obviously we will be using these constructs later, but I'm trying to keep things pretty simple here. So believe it or not, this is the shortest, I think, one of the shortest GPTs that you'll see. This could have been a bit longer because if you notice, I did use one thing here, which is the nn.linear. What is the nn.linear? So the nn.linear is like one of the basic building blocks of neural networks. But that's the thing I want to now, pay attention to this because it's pretty important, right? So I want to discuss now. So let's go back to the whiteboard. Go here. So what is nn linear? So NN linear is something from PyTorch. NN linear is something from PyTorch, where you provide some numbers, like you will say 4, comma 6. And then you do another NN linear, and you'll say 6, comma 3. Does that look familiar? We've done this before, right? This is Iris. So what NN dot linear does is it actually creates the whole equation of, you know how you get an X times W plus B equal Y, right? And so far in all my examples, I instantiated X and then I instantiated WQ or W and then I instantiated B. So I was doing this separately. Do you remember? So the best example of this was the attention, right? For Q, I created a W, I created a B, I created all that. When deep neural network frameworks like TensorFlow first came out in 2015, 16, you had to do that. You had to like create a tensor for W and a tensor for B. But that's already just in these three things, that's 3 lines of code. Do you see that this is already 3? Oh, it went away. We'll be back. Yeah, so as I was saying, when these frameworks first came out, you had to instantiate each one of these as its own tensor. But then it was 3 lines of code already, and then you had to do the matrix multiplication, map mul, and all that. They created a construct, this is the concept of encapsulation. This is probably the first time that you're seeing it in this course, encapsulation. It is not the last time. Encapsulation is actually the whole essence of deep learning today. So, for instance, libraries like Hugging Face, which we will, start to use in the future, encapsulate. What does that mean? It simply means you take code, 20 lines of code, and you make it into one, right? Or you take, in this case, let's say these 3 lines of code, and you make it into one. But it's all PyTorch. It's still all PyTorch. It's just, or it might be TensorFlow, but it's still just like the basic language, and you're encapsulating 3 or 4 lines of code and create a new element. Do you see that? And actually, you will see a little bit of this as we do the Huck Fin, where I'm going to create encapsulations such as head and other things. Okay, I might create an attention block, etc. So essentially, if you know object-oriented programming, it's kind of like that. Okay, so you can instantiate objects, etc. But it's got its own concept called encapsulation. So when you use something like the Hugging Face library, you can fine-tune a GPT with as little as 4 or 5 lines of code. But it's not because the underlying 300 lines of PyTorch code don't exist. It's just you're not seeing them because it's encapsulated. Okay? Does that make sense, guys? So your first example of encapsulation is, in fact, NN linear. All right? So inside, behind the scenes, there is an X, a W, and a B, and you can access them from the class. But it just does everything automatically for you. So it'll become easier for us to write the code. Do you guys see that? Does that make sense? Because that's what I'm about to do. It's like a function. It's like a class or a function or something like that that hides some lines of code, but they're always being done in the background. Okay, yeah. So matrix multiplication is definitely going to happen. You're just not going to be doing it anymore. Okay? All right, so that's going to be NN linear, and this is what we're about to do right now. Okay, guys? So we're going to go ahead and try this out. So I'm going to switch back. All right, so you can see this is the code. so that I'm going to go over, on the Jupyter notebook. We're already familiar with all these things. So this is creating X. This is the embedding and positional embedding. This is actually converting X to that. Remember that we added both of these, if you remember. And then here is your Q, K, and V. But if you notice this time around, I don't have to create the weights matrix, the bias, multiply them, etc., just to convert X to K. I can just directly do it by using NN linear. Okay, so I'll describe this in a second in detail, but I'm just saying it's just a simplification. And this whole mechanism, like these, I would say like these 10 lines of code are the attention. So you can see most of the code is actually the attention mechanism. Okay, very important. So and this is every block. So I do still just like before. I'm going to instantiate a Q, a K, and a V. Notice they're just like, as you said, like functions, and then I run X through them. Do you see that? Just like we did before. And now we have our KQV. Then we do our matrix multiplication of K and Q. And you already know what this is, right? So why did we do this softmax? That's a step that we did. And then after that, once we have the attention scores, we matrix multiplies with V to get the shape back. The only thing I didn't do here is I also don't have 8 heads, if you notice, right? And concatenate them to keep it simple. There's only 1 head. It's not wrong, right? Because we have at least 1 head that's paying attention. The difference in the full code is that we have 8 heads in parallel. So they're all 8 are doing the same operation, and then we concatenate. But this one just has the 1. Okay? And then here I have just a feed forward. This is like iris neural network stuff. And then this is the final, the output. And then this is the last projection where we map to the vocabulary itself, right? To a vector of 1,000 so that we know which of the words it is that we want. So if we had 50,000, then it would be 50,000. All right? And so I'll go over the code on Colab, but just to, I guess I want to wrap up this whole README. So what this does, essentially it's got the token and positional embedding. So convert token IDs to dense vectors, and we add the position. We calculate the KQV, which are really just linear projections. We have the attention weights, which is the dot product, and then a softmax, right, of K and Q. Then we do multiply by V. And then we do a feed forward. And then project finally another matrix multiplication to the vocabulary size. So that we'll see that in a sec. So this baby transformer has captured a lot of the core ideas of a decoder-only GPT. It's got self-attention, contextual token representation, feed forward, and the vocabulary prediction head, which we will see is the same with HugFin. Okay? So yeah. And then that's it. That should be, the output should be 2 by 10 by 1,000. What does the 1,000 represent? The 1,000 subwords. So this actually represents the word cat or tea or something. Each token in each sequence now has a predicted distribution over the vocabulary. All right, and yeah, that's it. So almost done with this. So now let's run through the code step by step. Even though you should understand every element of it, I just want to put it together, right? And we're putting together one block with no heads that takes an input and produces an output. And that's the whole architecture. All right, so let's take a look at the code. So it's going to be here, baby transformer in this Jupyter notebook. So I'm going to need some libraries here. Here. And please, if you have questions, this is a good chance to ask them because the next thing we do is the whole code, and that's a much bigger, right? So this one is still pretty approachable in terms of length. All right, so I'm going to do torch NN, and functional, which we've seen before. I'm going to set some parameters here, my config. So it's going to be batch size of 2, sequence length 10 instead of 40, vocabulary size 1000. Still using random values here, but a vocabulary of 1000. The embedding dimension is 64. So this is the thing that has been 512 before, okay? So it's 64. And there's a new thing, the feed forward. If you remember, we did from 512 to 2048 and 2048 back to 512. So that's what this is. So it's 128. Okay? So that's essentially the neural network. All right, so there we are. Those are the parameters. So yeah, baby GPT. So the first thing I'm going to do is just create randomly some integers. Okay, so batch size is 2 and sequence length is 10. So you can see them right there. That's my tensor that before has been 32 by 40. 32 by 40, here is 2 by 10. And this is exactly the input, right? Before this, what you had was text, okay? And then you use tick token to convert these integers, and you just have to make sure that you pad so that's total size is 40 or whatever it is, okay? Why 40? 40 was, most people would say, what's the average length of a sentence? Probably 26 at most, right? And then 40 seemed like big enough, right? And so remember that decision depended on memory and GPUs and things like that. So it couldn't be at the time 1,000,000, right? But wouldn't it be great if we could give a GPT a whole book all at once, right? And it pays attention to it. You see where that's going? So yeah, that capacity is important, but also it's, we're constrained right now because of our RAM limits and so on. All right, so you guys all agree that I took 2 sentences and converted them via tick token into integers, right? So you all get that. So it's text is coming in, okay, into the model, and we're gonna do all the transformations of this text now, okay? So the next step is to create my embeddings. You guys remember this part, right? So I needed to do one for positional embedding. We covered this last week, and one for like the semantic embedding or contextual embedding. So how do you do it? Well, a layer from vocab size to embedding layer. Remember that we said it's 1000 by 512 or 1000 by 64, right? Every ID is now a vector of whatever, 512 or 664. So that's what this one is doing. And then we have the other embedding, which is sequence length to embedding. So what's the size of this one? 10 by 512. Do you agree? Because there's only 10 positions, right? And each one of those positions will be represented by a vector of 512 or 64. But here we're just creating the construct, right? Like a function, right? And then now we run X through these functions. So I'm going to go ahead and I'm going to actually just run one first. I'm running the sequence of IDs, this one, through the embedding layer so that my output is no longer 2 by 10, but it is 2 by 10 by 64 in this case. So that each ID now has its own embedding. So that we can take a look at by saying xtoken.shape. Okay, run that. And you can see it went from 2 by 10 to 2 by 10 by 64. Any questions on that, guys? This was the previous concept that we had discussed. Again, remember, all these values are random, but eventually during training, these values get updated and they become the actual proper values. Now we repeat the same for positional encoding. We've discussed this one as well, right? So you guys remember this. We created a tensor of positions, and I'm going to print it out. Do you see that there? For every sentence, instead of the ID, like is it a cat or a dog, we have the position. Is it position 0 towards the beginning of the sentence, position 5 towards the middle of the sentence, or position 9 towards the end? Because, they are all of length 10. Okay? So once I have these values, I'm going to run them through the positional embedding. So now I run position through it and notice, and I want to print the shape. And I should have said shape. 2x10 by 64. Remember that the embedding and the positional embedding have to what? Match exactly, because you're literally adding them together, which, that might seem crazy, right? Like, you thought, okay, I get that this will somehow learn, but then I'm adding this. Isn't that distorting the value somehow? And as it turns out, it works, right? It works very well. So that's the idea. So now I have my two tensors, X token and X position. So I'm building a whole architecture from beginning to end. So remember, I took some IDs. Now I've created one version of it for token embedding, one for positional embedding. So that's done. Okay, now I'm going to go ahead and look at what I'm doing here. I'm going to add them together. So I take X token plus X position, and now there's just one single tensor, 2, 10, 64. And that becomes now what continues to go into the block, right? So all that we've done here, so if we actually look at, what I said before, go back to table of contents, and we look at the notes that I gave you that, remember, you have to read this. If we go to notes, we just completed this part and this part. We are like right here, right now. Do you guys see that? When I do the embedding plus positional embedding, I just finish this. And now this little blue arrow means I'm going into the first block. Each block has an attention layer and a feed forward layer. And a vector of n by 40 by 512 goes in, vector of n by 40 by 512 comes out, and then you can see you just repeat the process 6 times until the final layer. In this baby GPT, I don't have these 5. I only have the first one. Does that make sense? So I'm showing you, essentially this part, but we're just going to go into one block, and then we're going to directly go into the linear layer and out. That's the difference, okay? And then later next week, we'll definitely go to the full-on code. All right, so actually I have if you zoom in, I have one graph, I think, here. This one, you see, so this is just one block, and notice this captures the idea. N40 by 512 goes in, and 40 by 512 must come out. We do the multi-head attention. Why multi-head? Because there's 8 heads. We do it in parallel. We concatenate them. Once we get that final one, there's just a fully connected layer. From 512 to 2048 or whatever, and then 2048 back to 512. That's it. All right, so that's what we're doing right now. So I have my initial tensor 2 by 10 by 64, because that's what I'm using. Now the next step is probably the most detailed one, the attention layer. Notice here, is where I now start using NN linear, right? Could you write the whole Huck Finn code with creating weight matrices and biases? Sure. If you have time, do it actually. It'll work just the same, but you'll see that there's way more code, right, going on. And so this is really helpful. And then linear. So notice NN linear, essentially, we can map it however we want it. In this example, we're doing 512 by 512, but in the original one, it was 64, if you think about it. So you can also play with that. So this was, 512, this is 64. But we were doing 8 of them and then concatenating. Here we are only doing 1. So now I do instantiate WQ, WK, WV, all right? And I'm just going to create my KQV by running X through those functions. Okay, so let's do that. And you guys should be able to see that here. So once again, I create my KQV by running the X through each one. Exactly what we did before with the simplification of using NN linear. Does this make sense, guys? This is like a pretty important concept. No questions on this one? All right. So now I have QKV. I'm just printing K to see the shape. You can see it's 210 by 64. Okay. Now, what comes next? The actual attention score, right? That matrix should be of what size? 2 by 10 by 10, right? Because the sequence length is 10. Before it was 40, so it produced an attention score. So 40 by 40. This one should be 10 by 10. All right. So that's the next thing that we're going to look at. So I'm just going to grab line by line here. So this is the matrix multiplication, sometimes called the scale dot product with attention. If you look at the paper, actually, this is how they describe it. The scale dot product with attention. So that's from the Vaswani paper. But notice here, it's the K. Remember I said at just means matrix multiplication. So it's KQ. You transpose this. Remember we did an example in the tensor just to align it properly. And then I'm dividing this. This is like a regularization that's in the paper. Okay? So if we do this one and print the shape, two by 10 by 10. If I just, there's 2 of them. So if I just look at one, okay, so you can see there's values. I haven't applied the mask in this one. If you notice, I'm not doing that just for simplicity, okay? The mask should be added, obviously, but that would have made the code longer. In the Huck Finn one, it'll be there. All right, but this is just, so remember, this doesn't have the trill and all that. I'm skipping that. If you notice here, I just jumped directly to the softmax. So I didn't do that part that we discussed, but in the final one, it will be there. But I'm just, because I'm trying to keep it simple and just show you the flow of the tensor. So at this point, we did QK to produce the attention scores. If you remember, we had to run that through the softmax with the mask. But I'm skipping that here. So now you can see attention scores, which is this one, which is 10 by 10, is going in through the softmax to produce the attention weights. We can print this one. Oh, sorry, shape. You can see it is still 2 by 10 by 10. We've calculated it, but what do we need to do? We need it back to 210 by 64 or 210 by 512. How did we do that? With V, right? So we have our V, the KQV. This just takes it back. So now, oh, sorry, I didn't. So I'm going to take, notice the attention weights, this one after the softmax and the masking. What is the at sign again? Matrix multiplication. Matrix multiply it with V to produce the attention output. And then when I run it, 210 by 64. So it went from 210 by 10 to 210 by 64. And there you are. That's essentially the most simplified version of the attention mechanism. Okay. And now that I have this one, what comes is actually pretty easy, right? So let's take a look now. What is this step here? I'm creating two additional layers, FF1 and FF2. One goes from embedding to FFDIM, and then the next one goes from FFDIM back to embedding. So that's like, what I did in the previous example, where I went from 512 to 2048. You guys remember that? And then I went from 2048 to 512. And I just sort of made the joke, right, that they just add another layer for some reason. So, do you see that? So it just gives it more capacity is what I would say, but that's essentially what they did, and it's in the paper. And go ahead and read the Vaswani paper again, because they address this in a whole section, right? So you can find more answers there, but that's essentially what we're doing. In our example, this FFDIM, I believe is, what is it? 128? You guys see that? 128. So this is 128. So this, oops, would also be 128. And then what would this be in our example currently? 64, very good. So you can see it just maps it. And remember, we've already talked about it. Whenever we do these projections, etc., matrix multiplication is going from a space of 4 to a space of 6, back to a space of 3, and so on. Right? So that's essentially what's going on here. So I create these two layers, FF1 and FF2. They do have other additional little things like dropout, residuals, and things like that. I will talk about those later. It's just too many things are going on. Like the transformer has every possible innovation up to 2017 in there. Okay, so let's go ahead and instantiate these F1 and F2, or FF1, FF2. Okay, so we haven't yet run our attention output, right? We know it's 2 by 10 by 64. That's our tensor that's flowing through the neural network, but we haven't yet run it through these layers. So that's what we want to do now. So notice I just do this. This is essentially to just keep one line of code, because otherwise it would be several lines of code, right? Do you guys see that? This is actually, well, let me just copy the whole thing and break it apart, because it's several lines of code, but to keep it as one-liners, it's written like this. So let's do, whoops, FF1, right? So that's one. I'll get rid of this for now because it might confuse you. And I'm gonna get rid of this. Okay, so that produce, and then there's a ReLU. Okay. So this ReLU actually goes after that. And then there's an FF2, which goes after. So essentially, it's 3 lines of code. So we take attention output, right? Attention output is my, where I'm at, and run it through FF1. And this is like FF1 layer. Do you guys see that? And then FF1 layer goes through ReLU. Oops. So FF1 layer, and that just produces something else, like, let's call it ReLU FF1 layer. So these are just traditional neural network layers, and then ReLU. And then we have this one, which is the layer FFF2. And what does that take in? ReLU FF1 layer, just like that. And there you go. So essentially, that's all that's happening, right? So we're just doing it in one line, and we're running it, and every time, just think of it as X matrix multiplication W, a new set of weights. ReLU is actually the activation function. We'll talk about this one later, but think of it as very simple. So let me go to the whiteboard. Just think of a very simple example of what ReLU does. They call it the hockey stick function. So essentially values that go into ReLU. So ReLU is rectified linear unit, it's called. Hockey stick, so like that. So if from X, this is 0. So if it's negative, and this is plus. So, and this is the Y, you're transforming into this. So essentially, if the value on the X-axis is negative, it converts to 0. And if it's positive, it's linear. It's the same value, essentially. You let it go through. So another way of thinking about this is if I have a vector of the following values, -2, 7, 0, -3, 1, this goes into ReLU, and it gets converted into what? 0, very good. 7, 0, 0, 1. That's it. Literally, that's how simple these things are, right? So more stuff, the name is more fancy than what actually happens. But yeah, this is called they call it the hockey stick function, ReLU, and we'll see a ton of these. This is like softmax a little bit, but there are many others. But essentially, that's what happens. Why? Because they found out that this helps the neural network to learn better, right? And then there's several variants of this. All right, and we're almost done. So go back to a nice thing, a nice feature, you'll notice, we'll run our function through this. So remember, I'm making it 64 up to 128 and bringing it down, right? But essentially, when I run this, the shape is 21064. So you see this little game that they're always playing. 21064 goes in, lots of transformations, but 21064 must come out. Or 32, 40, 512 goes in, 32, 40, 512 must come out. That's essentially so that they can add the same blocks multiple times in sequence. All right, so we just did the projection, but notice the tensor is currently still 21064. So we need to do one last projection. So this projection is similar to when in Iris we did, you know how we did 4 to 6 and then finally 6 to 3, where the 3 mattered because it was the 3 classes of Setosa, Virginica, and versicolor. So here we're doing something similar, but for 1,000. Why? Because 1,000 words is what we have, or subwords is what we have in our vocabulary. So here the tokens predict the word finally. So you can see that the final projection to vocab. Embedding size is what? 64. But every one of these tokens, right? You agree that 10 is each one of these is a word, right? But they're currently in 64 embeddings. That needs to be converted into embedding of 1,000 and a vector of 1,000, which is going to be a probability distribution over all the possible words, which in this case is 1,000. So what do? And in linear, embedding dimension to vocab size. Okay, and then that's called to vocab. And now I take this one, the last from the previous step, FF output, run it through it. And there's, now I have my so-called logits, as I was telling you. And then here there might be like a softmax, etc., but I'm skipping that for now and just shape. And there you are. 210 by 1,000. Do you guys see that? That's a transformer. So we started, if you notice, imagine this is the whole transformer, the whole architecture. So we start with text. Then the text gets converted into n by 40 by 512, or in our example, 2 by 10 by 64, right? It goes through all those things, attention layers, feed-forward layers, but at the end, we get back n by 40 by 1,000, or 50,000 in this case, probably to be more correct. This would be 50K. Really big tensor, right? But actually in the scheme of the GPT, that's not big at all. And so what's important about this is, in our example, this would be 2 by 10 by 1,000. So for every one of these words, IDs, now we know. So it's like this. So let's say I'm gonna just zoom in on this one. And I'm gonna say, okay, sequence 1, 2, 3, 0, all the way to 10. 2, right? Do you guys see that? 2 is what? A vector of 1,000. Why 1,000? Because there's 1,000 subwords. So what you can expect is that this is a distribution, right? A probability distribution of which is the most likely word. So in this case, let's imagine that this is 17. If you have a really good model, what would you expect here? Let's go at 89. I meant 9, but I wrote an 8. So 89. And all these other ones then should be, somewhere around like 0.03, 0.05. They add up to 1, but you pick the one with the highest value. What does that give you? 17. And then what do you do with integers? You give them to tick token. And what does tick token give you? The actual word. Does that make sense, guys? Does this make sense? Any questions on this? This is beginning to end transformer. All right, once we start doing the Huck Finn one, you will see this in action. To keep it simple, Huck Finn only has 64 because it's the letters, right? So it's gonna at the letter level, but you need to although the assignment seems easy, you need to do the tick token part yourself. So you'll need to change that. Yeah, so I think that let's see, let's go back to here. All right, so we know for sure we got a tensor of 2 by 10 by 1,000. Yeah, and that's it. So I just need to print the shape. And there you go, 2 by 10 by 1,000. That is your logit shape, and that is your final tensor. At this point, what happens? At this point, that comes out, think of it as, and this is the last, we'll wrap up with this today, because it's really important now to think about this part. So what do I have? I have some text here that is converted into n by 40 by 512. It goes in through the whole transformer, and then you get, at the very end, n by 40 by, let's say, 50,000, 50K, right? But that's just going forward. So you gave it data. So you need to have now let's think of the training process, right? So you need to have what? X train and Y train. Do you see that? So the thing that goes in and the actual real thing. Do you guys see that? So then X goes in through here, goes through all this thing to produce, and let me change color here. Let's call it Y pred. What is Y pred? This guy over here. And then what do I do with that Y pred? Because really I just transformed a tensor that came in, right? With random everything, right? You agree that everything was random. So, but once this Y pred comes in, I compare it to what? To this Y. Do you guys see that? And that's your minimization of error. At this point, this predicted is compared to this one, right? And you measure the difference. And then what do? Based on that error, you back propagate. You use the stochastic gradient descent algorithm, right? And you optimize all the weights, layer by layer by layer by layer, until you get to the beginning. And then now you have no longer just the random weights. You have the random weights plus a tiny update. And what do you do now? You grab another chunk. So imagine I'm grabbing from books like Shakespeare and Huckleberry Finn, these X's and Y. We'll see this in the Huck Finn, how this part, because in there we'll train, right? So what comes now is the training. Here I haven't done training, but in Huck Finn we will. And understanding that might be a little bit tricky, but we'll get to it. So you grab your X and Y, and guess what? I'm going to change color here. So now X goes in, right? This chunk of N40 by, a new chunk of N40 by 512. You run it through the whole thing. What does it produce? N by 40 by 50K, right? But another, corresponding to this one, a transform one. Now, where these weights that you used in this second iteration are a little bit better, right? Because they were the random plus a little bit of an update. And when this happens, you produce Y pred. And then what do? You compare it to this Y from your training set, right? So that's Y. So this is, you compare, and what would you expect? Now the prediction of this Y pred is a little bit better than this previous one. Do you see that? So you compare it to this, back propagate again. And what do you do during that back propagation? Update the weights a little bit. Which ones? All of these. Think about all these matrix multiplications that we've been doing, right? And that's just a baby GPT. Wait until we get to the actual Huck Finn one. It's massive. That's why it's massive. Like 7 billion parameters is small, right? And then, but the weights got updated a little bit. And then what do? Change color. Go with this one. You graph another book from Huck Finn or Shakespeare, another chunk of X and Y. Convert it into N40 by 512, goes in here. Transform it. N40 by 50K comes out. Right? That's your Y pred. Compare it to this Y. Minimize the error. Now, what would you expect after many iterations? This is starting to sound like English, at least. Then it starts to sound like English, but it's got good grammar. Then you ask it a question and it's like a good answer. You see where I'm going with it. So it starts to improve by that process. And you take the difference, use stochastic gradient descent to back propagation and update the weights further. The magic of this is you take this architecture that we're discussing and you give it all the data in the world, all the text data, and 50,000 GPUs and 6 months of training, and it learns something. Any questions, guys? Perfect. So this is a good stopping point. We're going to stop here for today. We finished baby GPT, all that. In the next session, next week, Huck Finn. So if you want to start, so you have a lot of reading to do. And also keep in mind the exam is coming up. This is week 4, I believe. Exam 1 is week 6. So it'll cover LLMs essentially, right? Everything that we've discussed. So your reading assignment, you now have homework, which is the crawler, right? Start collecting your data. That's been assigned. You know that the next assignment will be this one. I will cover, so next week, I will focus entirely on Huck Finn and this book. So we're going to take The Adventures of Huckleberry Finn, and we're going to train a GPT from beginning to end, and this time it'll have everything. So make sure you study everything so that's easy to go through. Resources for you guys, all the code I provided, obviously, and then these links. Remember, you should take a look at notes. You should take a look at the Vaswani paper, which is the original transformer paper, to help you out. Got it? All right. So yeah, let's stop here for today. I'll say a few minutes if you guys have questions. Otherwise, I'll see you next week.